Alrighty, welcome back, everyone. I hope you're having a great time. We've managed to get some great food. It's certainly a treat for me. I've enjoyed that. And I hope you have casted your vote for the best student poster, because we will be awarding prizes at the end of the day. I would now like to introduce Dr. Vladimir Lisitsin. Vlad is the manager for the Mineral Systems team at GSQ and holds a PhD from the University of Western Australia. He brings over 20 years of experience working in geological surveys, both in Victoria and Queensland. At GSQ, he leads a diverse group of geoscientists dedicated to extensive data acquisition and research, focused on characterizing key mineral deposit types across Queensland. Please join me in welcoming Dr. Vladimir Lisitsin.
Thank you, Heather. Thank you all for coming back from lunch. In this presentation, I will give you a very brief overview of our mineral deposits and mineral system characterization program at GSQ. So that's the main focus of our team's work for over 5 years. And I'm speaking on behalf of the team, and most of the team is sitting there on the background on that. And this is we have a nice display that we'll call from the book. Instead of showing examples of some specific data, some information required recently, I will focus on trying to synthesize the information we have collected with our numerous collaborators over the past 5 to 10 years, present some regional metallurgical models focusing on the Intrusion-related mineral systems. So GSQ, with our multiple collaborators, we have spent the best part of the last 5 years characterizing deposits and mineral systems, mostly in North Queensland. So our work starts in earnest in North-east Queensland, where we started our work back in 2018-19. We have started our focus on North-east Queensland several years later. And to date, we have covered more than 80 individual deposits representing more than 10 individual mineral system types. So we have a good collection of data which we can discuss with confidence. And the focus was specifically on North Queensland because that's the primary mineral processes, North-west Queensland, Mount Isa, and North-east Queensland with this various innovation styles. But the intent is to roll out the program and cover the entire state so that we can speak with confidence and present consistent comprehensive data sets to address all mineral systems of note and all deposit types of significance across the state. And one point to keep in mind is that even though the work of deposit characterization is focusing on deposits, but the actual intent is to provide regional coverage to characterize the entire extent of each significant mineral system, so that we can use this consistent information for regional exploration and mostly not us using it, but presenting that information and learnings to the industry for them to pick it up and use it. So in all deposits which we study as part of the program, there is a consistent workflow. It all starts from understanding, collecting fundamental information about deposit geology. Lots of this work in recent years has been done by University of Queensland. We have several phases about the program of deposit atlas. So I'm pretty sure most of you will be well familiar with it. And if you haven't checked, it's a wonderful source of information. So we're using compiled information on deposit geology to select 2, 3, several representative drill cores per deposits. We systematically study them, starting from follow the drill core scanning, sampling, follow the chemistry, and doing more detailed work with ever increasing level of detail and complexity. And a little bit of a more detail of us, which kind of data acquisition we're undertaking. I'm not going to stop on that in great detail because Elena Belousova has a presentation this afternoon, and she will illustrate individual data acquisition methods and tools we're using in much greater detail. So as one point I want to emphasize again, to keep in mind that's the points of this systematic characterization and data acquisition deposit by deposit is first to provide internally consistent data sets, which allows us comparison between deposits and between mineral systems to make sure that if we document any differences, they are real, they represent some geological differences and not artifacts of data acquisition. And so we always intend to take the data for individual deposits and roll it up, synthesize it at scale of the entire mineral system. And that's what I'm going to illustrate from this point onwards. And attempts to synthesize, illustrate combination of knowledge of individual deposits on regional scale. So let's focus on North-east Queensland. So the area of interest is defined here, starts just to the south of Townsville. That's the main geological reason of doing so. First, we're focusing on the area north of mineral origin. So that's the area focus at lower card in classification. New England origin, the bulk of it has a distinctly different ecology, and the distinct ecologic belts largely with porphyry copper specialization, intrusion-related systems runs all the way to New South Wales, and we need to stop somewhere. So it was the best for us to stop. Just getting the northernmost parts of the New project. Within this region of North-east Queensland, there is a great variety of deposits of different commodities, different styles and types. There are at least 16 distinct types of mineral systems, and you will see that lots of the area is covered by gold deposits of different types of styles, both intrusion-related and orogenic and epithermal. There are several pockets of tin and tungsten deposits in several districts. And in this presentation, I'm going to focus only on deposits with either demonstrable genetic links with intrusive magnetism or with strong likelihood of or at least spatial association with intrusive magnetism. And that's one point to start with. Because gold deposits are particularly widespread and they're particularly diverse. They're covering this entire region. So this entire region can be described as A grades gold deposits. So we'll focus first on intrusion-related and epithermal gold deposits and exploration. So there's dominantly gold deposits, they're mostly very concentrated around Regisford Pathway, Characterisation province, and in Georgetown, and in the outskirts of the southern Cape York. So that's where we're going to focus the rest of the conversation. Gold deposits are present in varieties of types and styles. So there are native gold deposits sitting in above 2 tons in cornfields, host rocks. The most common ones are different styles of vein deposits, including even low deposits of shallow veins, steep veins, astrophils. There are breccia pipes. There are porphyries, and there is nothing wrong about used to develop porphyry gold because they do look completely and they are actually porphyry gold. And there are some gold deposits, so that was a cover this next. So once we reviewed the complexity and variety of deposit styles, we did systematic characterization of geochemistry in particular. So this is the only bit of actual data information which I'm going to show in this presentation. This illustrates overall geochemical signatures of different types and styles of deposits. Essentially, the basic take-home message is deposits of different geological types that have distinct overall geochemical signatures with some overlaps. And where overlaps exist, that's a good indication, good suggestion of genetic links to deposits, and that's something which we can confirm in other ways. And as one of the points of doing systematic geochemical characterization was to consistently document comprehensive geochemistry done to the same standards for all the deposits. There was lots of industry data available, but most of the actual raw information is not accessible, and there are big artifacts of comparing deposit geochemistry when it was done for a period of 30 years with different companies. So we can speak with confidence about similarities and differences of overall deposit signatures and any variations in information within it. So attempting to synthesize everything data and knowledge we have accumulated over the past 10 years. This is a relatively busy diagram, and that's a nice introduction to the history of this diagram. I'm pretty sure everybody who's working in intrusion-related code systems in North-east Queensland is well familiar with precursor diagrams of this nature, which they were produced and publicized by Greg Morrison and used extensively by industry researchers. And that's one curious bit to note that the first version of this updated diagram was produced by Greg Morrison during his first project with GSQ during 2013-14, and it was first publicly presented at the PDP seminar in December 2014. So it's very appropriate to 11 years later to present an expanded and updated version of that at the DPP event. So the basic message of this diagram is that the variety of deposits, styles, and types in North-east Queensland, so they can be genetically linked to intrusive magnetism of a particular type. So the variety of deposit styles are largely a factor of the depth of emplacement, fluid pressure, and physical and chemical properties of stocks. There is a good message to take from here. Intrusion-related deposits are defined as those which are formed by magmatic fluids. It is mostly correct, but not entirely, because as time goes by, more information comes to light of transitional members between pure and magmatic and mixed fluid sources. This is particularly common in bottom part of the deposition spectrum with depths of 6-7 kilometers, where it's not uncommon to have mixing between magmatic fluids and metamorphic fluids, and there are very common situations of fluid mixing of magmatic and meteoric fluids that have shallow levels. And one of the key characteristics of intrusion-related coal deposits, one of the defining and recognizing criteria for them, is geochemical zonation as function of distance to host intrusives. It's particularly well pronounced in intrusion-related coal deposits relatively proximate to causative intrusions. This relationship becomes much more difficult to recognize in areas of common fluid mixing zones, both in zones of mixing with metamorphic fluids at the bottom, and very distal deposits like most thermal gold deposits, low saturation of thermal gold deposits in shallow areas. So this is the dominant family of deposit styles and types in North-east Queensland. That's a useful thing to note that in the same area as there was Intrusion Lake and consolidation of thermal gold deposits, there is a great variety of deposits of other mineral system types and different commodities. And there is a remarkable property of synchronicity of different deposit types and different mineral system types forming in adjacent areas at exactly the same time. So there are clearly several well-established interdependent books, and we can just be right further into episodes. But for brevity, I'm going to go into that level of detail in this presentation. So, for example, in particular, in the early Carboniferous 350-335, so this is the first pronounced appearance of reserve intrusion-related gold deposits. That's introduction of Keystone, for example. And at the same time, there is epithermal gold mineralization developing in the Grand Basin, Virginia. And so the earliest phase of orogenic gold mineralization in Northern origin, and the earliest introduction of tin mineralization in Kimberley Hills. So the next episode, which is mid to late Carboniferous, that's where the bulk of intrusion-related gold deposits are introduced in pretty much throughout the region. And at the same time, we see the introduction of just about all of the tin deposits in the Everton district, and introduction of these more the tungsten rising deposits, and the main phase of introduction of the course of free gold, orogenic gold deposits in the Petrophysics deposits. And then finally, the early Permian episode. That's the most widespread gold mineralization throughout the region. That's where most of the thermal gold deposits formed from near the tip of Cape York down to Mount Carlton. And at the same time, we saw the introduction of tungsten deposits around Mount Carbine and tin deposits around Cooktown. So this synchronicity of introduction of different deposit types and different mineral system types in the adjacent region creates an impression of their likely genetic links. We're not going to explore all the genetic links for all these deposit types. We will just focus on the most close, those ones most closely related to intrusive magnetism. And this can be best understood by revisiting, reviewing some, and recycling some diagrams introduced a long time ago. So one of them on the left is the diagram describing all the families of intrusion-related, granite-related deposits in the seminal papers of Tompkins et al., Thompson et al., Professor Lane, Baker. So this was the first, to my knowledge, introduction of the concept on a single diagram, showing the location and places of different granite magnets in terms of their fractionation and oxidation state, and their metallurgical specialization. So this is the main focus of this diagram originally was to show the field of intrusion-related gold system, which at that time was a very controversial mineral system model was still new. And this mineral system model was still fighting for its survival throughout 2000s. And it also carries two other very important deep bits of information. Namely, it highlights very distinct tectonic positions of oxidized and relatively primitive magnets with copper moly geological specialization of both the coppers compared to the granites which are producing tin, tungsten, molybdenum, and gold deposits. So both the copper deposits and their parent magnets are forming in magmatic arcs, mostly on the primitive crust or overprinting the outer outskirts of the continental crust. Tungsten, moly, and tin and gold deposits are forming deeper inland in parent continental crust. So there are not much of a transition between these two groups, and they rarely form in the same place at the same time. Conversely, that's the extension of the use of this diagram for tin, tungsten, moly deposits can form in adjacent areas and even in the same plutons at the same time. And they can form a progression of deposits with evolving combination of commodities even within the same magmatic. And the diagram on the right is well known to most. It's just a reformulation of the same concepts interparameters which are easier to measure by geochemical characterization of granites. This was first introduced by Phil Blevin as part of the Myra project in the 1990s, and this version was published in 2004. It also identifies the area of the field of compositions which are fertile for intrusion-related goals. And also the one of the interpretations of this diagram is that there should be, there are transitional members of magmas which can produce tungsten and molybdenum and gold deposits as part of the same events in the same place. So now an attempt to introduce a very complex diagram which shows probably that's a useful illustration of the lithology of the area around Herberton district and the adjacent areas in gold deposits. Essentially, it means that at the same time, during the same magmatic episode, you can form intrusion-related gold deposits from magmas which are slightly less reduced to slightly oxidized and slightly less fractionated. And in another part of the same igneous magmatic episode, you can form pure tin granites which are strongly reduced, strongly fractionated, and they're producing deposit types technically of a separate mineral system type at the same time. And so there are places where the degree of oxidation and fractionation is such that these systems can produce hybrid deposits, either gold deposits strongly enriched in tin, or conversely, tin deposits, tin without deposits, anomalously enriched in the gold compared to ours. And the curious observation here is that tin granites can produce deposits of essentially the same types and styles as intrusion-related. You can take the image of some deposits of tin mineralization, recover them, and so you would not be able to distinguish them from intrusion-related gold deposits. Probably the only significant difference is that tin and tungsten deposits, they are much more likely to form mineralization internal to their host plutons. So hence the commonality for tin and tungsten granites of the deposit types like granites, which are quite common in this. Similar to other intrusion-related systems, tin granites are producing deposits and camps with characteristic geochemical zonation at a scale of hundreds to thousands of meters. It's the same geochemical kind of geochemical zonation as for intrusion-related gold, but because of the differences in the original magma, there are differences in chemistry of hydrothermal fluids, there is a different composition of a different combination of elements which are precipitated with distance to positive influence. And one important common characteristic between tin systems and intrusion-related gold systems, particularly interesting to me, are their crystal products. That's where they start losing their direct links to causative magmas. Quite often that relationship becomes equivocal at best. But this could be the best signatures on the ground of the presence and activity of a mineral system. So with a high likelihood of good deposits of different kinds and sometimes of different composition of commodities. And I think that's all I have time to say about this synthetic model of intrusion-related mineral systems regardless of commodity. A little bit about advertisers feel for specifically for intrusion-related gold and for the core workshop, which we're running tomorrow and on Friday. We're going to have some 50 people turning up, and we're going to show the entire range of intrusion-related gold deposits from porphyry level to a very shallow dome. If you are coming there, you're welcome. Happy to see you there. If you have not registered, please come and talk to me. We can engage like this. And I need to acknowledge the great contributions of multiple people and groups who helped us develop these ideas and concepts. In particular, Greg Morrison from Exploration Services. We've worked with Greg for the best part of the decade since 2013. Under one line, and then has multiple collaborative projects. Research, the most integral part of doing work in Characterisation region and Georgetown. So we started our work with Eagle James Cook University in 2014, and there were like dozens of research students and postdocs and senior researchers working with us on multiple projects for the last 10 years. We're increasing our collaboration with the universities, largely for their laboratory services. And of course, we're very grateful to all the companies which were willing to share their data and knowledge with us, and this group is growing. Thank you for listening.
Are there any questions? Okay, thank you. Our next speaker is Dr. Elena Belousova, a principal geoscientist at GSQ. Elena graduated with a BSc Honors in Geology from Kiev State University in 1988, and then went on to complete her PhD at Macquarie University in Sydney in 2000, where she studied trace element signatures of zircons and apatite across a wide range of rocks and mineral deposits. From 2000 to 2021, she's held positions as a postdoctoral research fellow, senior lecturer, and then as an associate professor in the Department of Earth Planetary Science at Macquarie University, contributing extensively to research and teaching in geoscience. Today, she brings her expertise and research experience to GSQ, where she continues to advance our understanding of Queensland's geology and mineral systems. Please join me in welcoming Dr. Elena Belousova.
Thank you, Heather. It was a long introduction. Thank you so much. Well, today I would like to start my presentation, if I can start it.
That's a good one.
Okay, I use this. Yeah, okay, thank you. So I would like to start it with showing our Queensland map, very simplified map with just some colorful dots. And I like it because it shows you the distribution of our critical commodities across the state and their concentration in the eastern part and northwest Queensland. In northwest Queensland, you can see the clustering of the blue and orange dots, and they represent our copper and cobalt. And also I show the map of the northwest Queensland, just to emphasize the range of the deposit types in northwest Queensland. And also in my presentation, I will show some examples of the samples we're working with from northwest Queensland, and also to make sure I mention copper and cobalt in my presentation. If I don't, just remind me. But also the main point is just to show the variety of the deposit types and our approach to characterize the different deposit types in different systems in a consistent and comparable way between the northeast, northwest across the state. So Vlad already mentioned about our detailed characterization process starting from the core whole of geochemistry. And today in my presentation, I would like to focus on our microanalytical work and focusing on the new and advanced instrumentation and characterization process we use in new acquired advanced instruments, and you can see some of them I put on this slide. So before I start, I just wanted to say that we probably need to justify why we using this detailed work, time-consuming and not cheap exercise to do this detailed characterization. And I think if you're in exploration, I can put a lot of dot points what this information will help to refine you. So if you're looking at the detailed mineralogy, including some rare and accessory minerals, you need this. If you're looking at the progenetic association of these minerals and alteration signatures of deposits, again, this is a better instrument. Critical mineral developments, in situ geochronology or mineral geochemistry. That's where you need your base, you need your understanding to dive into this. And without this information, now it's very hard to constrain your model for any mineral system. So this is my justification. In the next few slides, I will show you just different type of instrumentation and what sort of information we are receiving and what sort of data output and what is published, what is coming. So the first one is our LEAPS exercise, which we did in a close collaboration with AXT. So LEAPS stands for laser-induced breakdown spectroscopy. So these instruments, they have a couple of different instruments. Some instruments can do the core scanning, it's LEAPS Echo instrument, and the other one is LEAPS Curiosity, which mainly focusing on a relatively large samples. Very nice technology. It's a very fast scanning. It doesn't need a lot of preparation. That's why we could scan trace and trace of the core. But the most important probably benefits of this analytical instrumentation is the capacity to analyze some light elements. And we know how difficult to analyze lithium, boron, and this sort of light elements with any other analytical equipment. So just to show you example what we can gain, this is our tray, and maybe I should, before I jump into this, I should show that we scanned 35 trays from a range of deposits from both North-east and North-west, and the report is actually in preparation. We hope to release this data by the end of this year. The other work we've done, we actually had one of the instrument and EDC for a couple of months, and we went crazy and we scanned about 500 samples. So this is still a backlog of data which we need to process, and we hope early to mid next year that will be processed and data will be released. Just to show you example what LEAPS can do. So this is the example of the tray from the North-west deposit, Maroon and Broken Hill type deposit. And you can see this is an image from the high logo where the colored dots are representing the different minerals. So even from this image, you can see how complex the mineralogy here, the textural elements you can see, and the range of mineralogy. But if you look now at the tray, the same tray scan using the LEAPS technique, you can see not only very detailed mineralogical information on this, but you also see some textural elements. It's really complete information for your logging and for your understanding. And also if you're focusing in a particular part of the deposits and further characterization, it's the best sort of information to choose the area of interest for your whole group analysis, for your geochemistry, for your isotopic work or geochronology. Another example is our long-term collaboration with SARU, where we use the Maya method instrument, which is the micro XRF instrument with a very high resolution. So over several years, we've done not as impressive number of samples as we did with LEAPS, but still this is a very slow technique and a very high resolution. So we've done quite a few samples from North-west Queensland and and not as many, but still 11 samples from North-east Queensland. Again, an example of the Maronan sample where you can see distribution of the iron, zinc, and lead, and you can see how fine details. You can see the distribution of these individual elements, but also you see their phylogenetic relationship. So the data we collected is in collaboration with CSIRO. It's now released. We released it early in this year. So if you have some deposits with which skin, you can download this report on our, which is available on our open data portal. Well, the next instrument is probably our pride, which is we have our own tornado instrument, and it was really, really well used. It's not destructive method. It's required relatively minimum preparation, still some polishing needed. It can scan quite large samples. You can see the dimension there up to probably 19 centimeters long. It has quite a reasonable resolution down to 20 microns, so and a good range of elements. But what is particularly nice that during our sampling we can do active, analytical work. We can bring it in and look at the individual and do the spot analysis very quick, very fast to refine what mineral we dealing or any question we have in terms of the composition of elements in present. So we scanned over 400 samples by this time, and Tamini and Alkis are probably the main users of these instruments. So well done, guys. And most of these samples are processed, and where we, in terms of producing the element of individual or combined multi-elemental maps, most of the data are processed. But this be capable to produce some mineral phase maps, and it's more involved processing, and we really behind that. But in general, we think that even these elemental distribution maps would give enough information in many cases. And one of the sample I show here is a distribution of sulfur, copper, and cobalt. Remember, I remember to mention. So it's really a nice example where you can see that cobalt and sulfur, which is mainly represented by pyrite, is not coming together. So it's not always that cobalt associated with pyrite. In the next slide, I show you example of those single element maps. And this is a sample from one of our RSG deposits, it's Rocklands, and this is the milled polymictic fracture. In this sample, we know from the whole of geochemistry, this is from the interval with high copper and cobalt content. So you see the first image. This is actually the photo of the sample. Then you can see the distribution of sulfur is mainly your pyrite distribution, your copper, where you have charcoal pyrite. You can see this rounded class of actinolite altered material and really nicely highlighted by magnesium composition. And here's your blue, your cobalt. So, and you can clearly see in this case, cobalt really nicely correlates with your pyrite distribution of the pyrite in this sample. And it's actually how nice it's correlated perfectly with arsenic distribution. So I think it's enough information. You don't need sometimes, the mineral maps. But if you do, we do the next step. We pick up the area of the interest. Remember this region in the sample where we have high cobalt content, but we can also look at the more details of the mineralogy. And here we're using our automatic mineralogy, the instrument, TIMA instrument, which is we are using at the QVT labs. And we can actually get very, very detailed mineralogy information, including information on the accessory minerals, but also the detailed even variation in a single major rock-forming minerals. In this case, we show the actinolite showing zoning in magnesium and iron, and this was verified by electron probe work. So this sort of workflow and also our building the library and identification process and verification process is now published in Minerals, so it was accepted and published very freshly just last month. So if you're interested in the process, how we do it, please look out for this paper. Another example is our cobalt department investigation. So in some samples, this is one of the sediment hosted copper deposits where we see it's 1,000 ppm of cobalt. And in this case, when we look closely, looking at our TIMA, you can see the zone in TIMA, and then we can look at the fields in TIMA in more details. We can see a range of the own cobalt minerals, which is not the cobalt, which is not associated with pyrite, but forming tiny little grains of corallite, linear sometimes, and you can see this very clearly cobaltite trace on the pyrite. So this is the power of this high resolution microanalytical work. Another aspect, useful aspect of the microanalytical work at Tornado is just looking at the multiply generation of the mineral and the alteration paragenetic relationship. So this is the samples from the Rocklands deposit, and you can see in the hands, this is and the hand specimens, you can clearly see the multiply cross-cutting relationship where you can start put together your mineralogy in a cross-cutting relationship. But looking at the tornado image, it makes it so much easier to recognize and clearly identify the phases and set up these paragenetic sequences, which resulted in this kind of diagrams where we have more confidence with all this instrumentation that it's correct. But another point I wanted to make with this particular diagram, that in many cases, in many deposits, we have multiple generation of the individual minerals. And it became very important when you're looking at the vectoring and you're using specific minerals. So then you clearly understand your direction of your vectoring if you do it. Or, for example, if you do your in situ isotopic, you want to do it on some sulfide which is actually associated with mineralization, not something which is predated and could be related to original event. The same is relevant when you try to focus and date your mineralization. So if you take your appetites, which is actually could give you information on the regional and early events, it could be totally different to the age of the appetite, which is in the association with actual mineralization. And just the next slide just emphasize that here, in this case, you have your appetite, which is in a clearly very nice paragenetic relationship with the chalcopyrite. And you can see also that this chalcopyrite came quite late. It's in field in the magnetite and the pyrite. So that's how we use this to just improve our cross-cutting relationship, mineral paragenesis, and targeting the right minerals for the in situ. So what we do with all this data, we have a lot of images and a lot of data. How we put it together so it's useful and sort of industry ready. We think we can improve our deposit atlases, and we can just add this information and upgrade the available 3D models in the deposit atlases, where you have your regional geology, where you have the deposit shell. In this case, this is the copper shell. We can zoom in and look at the drill core, which we started using the high-low instrument. We can zoom in and look at the individual trade. We have the high-resolution images. And on the top of it, we can put our microanalytical work. So if you want to look at the detailed distribution of individual elements, it's actually in the context of the drill core of the deposit. So I hope that would be much more useful information rather than individual images. I think that's it for me. Thank you so much.
Are there any questions? All right, thank you.
Any questions, please come and answer.
All righty, our next speaker is Roger Cant, Senior Geophysicist with the Geological Survey of Queensland. Roger's technical leadership covers everything from design and field implementation of gravity and magnetic surveys to the integration of resulting data sets into broader geological frameworks. At GSQ, Roger also takes a lead role in geophysical data management and delivery, ensuring that complex geophysical information is accessible and well interpreted and directly supports exploration, mapping, and resource evaluation across Queensland. Please join me in welcoming Roger Cant, a go-to expert in geophysics, a data champion, and a strong technical leader in Queensland's geoscience community. Go, Roger!
Thank you, Heather. All right, integrated Petrophysics data with GSQ's reference collection data, new data from the FPL project. So as Elena and Vlad have been speaking about, the reference collection and characterization project has been going on here at GSQ for more than 5 years now. And it's focused on determining the geochemical and mineralogical signatures of mineralization and alteration of key deposits here in Queensland. With all the effort that's being put in by the team to beg, borrow, and steal core for these deposits, it's only right that we extract as much information as we can from this core. And so the decision was made to acquire a suite of petrophysical measurements from as much of this core as we could, especially because there's such a void of data when it comes not only to petrophysical data on core hole, but also downhole property petrophysical data, especially in the mineral space. And so most of this work was focused on the northwest deposits that have been characterized. Why should we care about petrophysics? Petrophysics is, of course, most commonly thought of as the link between geology and geophysics, but it's just so interrelated with mineralogy that it just is such an obvious complementary data set to add to the reference collection. Physical rock properties are often consequences of geological processes in a local mineral system. And so it's very useful to have data specific to the area that we're working in so that we can feed that into your conceptual geophysical models. There is, of course, a lot of natural variation in physical property data, particularly when it comes down to your magnetic stability and electrical properties, which is why it's important to collect quite a substantial amount of measurements in order to have good representation across your geology. This data should ideally be collected in conjunction with other robust qualitative geological information, such as lithologies, mineralogies, metamorphism, alteration, weathering, as well, of course, as some more quantitative data, such as the grain size and porosity. And finally, similar to our high logger and mineralizer workflows, we really wanted to acquire a data set in an automated fashion with as little human bias and input in the sampling process as possible. And so cue the Mobile Petrophysics Laboratory. This is a collaborative initiative between CSIRO, Ozscope, the NCRIS, and the University of Melbourne, and the MPL was found to be the ideal tool for the job. The data promised to be, and I quote from the website, precisely co-located, meaning that there is a great number of opportunities to reliably augment existing mineralogical and geological data sets via more complex and machine-based algorithms to facilitate multidisciplinary approaches towards characterization and modeling. Perfect. The containerized petrophysics modeling system had just done its first stint down in South Australia and was ready for deployment to a new, more tropical destination, namely Zilmere, Brisbane. And so work began in July 2023, and after a week of long training and a week-long training and induction exercise, it continued through for the entire year until July 2024. During this time, drill core from over 30 mineral systems was logged at 5 centimetre intervals from representative sections of host rock, alteration and ore zones where available. These deposit names, they might be readable from there. But if you supply GSQ with any core in the last 24 months for the reference collection, chances are we've got at least a couple of hundred measurements from your core. All up, we collected around 18,000 co-located measurements. Together with the team at CSIRO, these are now being processed and composited with high logger data and, of course, any other information that we have on hand. Right, a little bit about what's in the box. The tool in there is the Geotech Multi-Sensor Core Logger, or MSCL. While the physical property measurements all happen automatically, with, of course, the contact sensor mounted on motorized arms, the drill core still needed to be loaded manually onto plastic boats, which are then pushed through the logger and then manually replaced back into core trays once logging has been completed. The core is loaded on the right-hand side here of the logger, which is then pushed in by a laser-guided electronic core pusher, and that's a very high millimetre accuracy, so we know exactly whereabouts in the core we are. The first measurement is made by the attenuated gamma tool to give us our density. This is equipped with a small cesium gamma source above, and there's a receiver below to determine the density via the decay counts. Next in the sequence was an ultrasonic velocity tool, which measures the P-wave velocity with a pair of transducers mounted horizontally, so they come in and contact with the core and send a sonic vibration through there. There was an optional extra to have a portable XRF in the workflow, which we decided to do for completeness, and to enable a future comparative study, potentially comparing results with a lot of the mineralizer data that was collected on some of those cores as well. Following that, there were two MagSUS instruments, one point sensor and one loop sensor, the loop only being really useful for the whole core. And then following that, a non-contact electrical resistivity tool. And finally, at the very end there, natural gamma tool, which measures the potassium, uranium, and thorium counts, which are the three big cylinders around it there. Each of these sensors was positioned along the logger to enable simultaneous acquisition of measurements in order to optimize how much core could be logged at the same time. The speed of the acquisition was limited mostly by our PXRF, which took 40 seconds per measurement, compared to most other sensors, which can usually complete a measurement in under 10 seconds. All right, on to some of the data. Here we have what's called a Henkel plot in the top right corner there, with your density on the x-axis and the logarithm of your MagSUS and your susceptibility up your y-axis. It's a very useful thing to be able to tell you, if your unit of interest, how it's going to respond to potential field geophysical measurements. And there's been a lot of work done to establish these trend lines here. So you've got your magnetite trend line up, black line here, and then your red one, which is your paramagnetic trend. The plot down here contains all of our co-located density and mag dust measurements, which is why it's such a mess. There's over 18,000 points plotted in there. And they're coloured up by mineral systems. So we've got some IOCG systems plotted here in the red and orange. And as you can see, they very closely follow the magnetite trend as you'd expect with an abundance of magnetite in most of those systems. While your sediment hosted and metamorphic systems follow the paramagnetic trend. And they're in the yellow and the brownish colours in there. The Henkel plot is also very valuable as a quick look QA/QC tool, as most of the data will plot within this predefined area we see in our Henkel plot. And outliers can be identified very quickly, especially when there are large populations that are plotting outside that range. And of course, one of the challenges of logging the mineral drill core is estimating the thickness of the split core correctly. This is a critical factor in getting accurate density values using the attenuated gamma sensor, as the processing from counts to density requires a volume calculation. There's also alteration due to the extra surface area exposure to split core, which is likely to cause a lot of this spread that we see in our all samples plot over here, which is why it's useful to look at our whole core measurements to see clearer trends in the data. It's also confirmed the presence, as you can see, of sulfides in these holes, which we can clearly see sticking out, and sensitive to what we see in the Henkel plot, this line here following your pyrite and chalcopyrite out here. The measurements to the left of the curve as well in the blue were from some highly porous old basement samples, hence their decreased density values. So we're not too worried about them falling outside of the plot. Some other notes are that some of these samples do have a negative magnetic susceptibility response, namely pegmatites and carbonate-rich rocks. This is due to diamagnetism. And as you can see a couple of them plotted in turquoise with a square sort of circle. The other thing to watch out for, as always, when looking at magnetism, is any remnants component that's going to affect your total magnetism value. The acoustic impedance plot. Similarly to the Henkel plot, it can tell you if there's going to be a large enough density and velocity product contrast in your lithologies of interest to be able to image interfaces using reflection seismic methods. This can be done by looking at these reflection coefficient lines plotted along here and ensuring there's at least one full width separation between your units of interest. There are quite a lot of theoretical values for both minerals and rock values, as shown by the ranges in the top plot. And you've got your sulfides clearly plotting out to the side to the right of the Nace-Drake curve, which is this grey line along here, along which you'll find most rocks plot. And as you can see, that's well done in our whole core sample plot. Alteration, minerals will attenuate a lot of your velocities, which is what causes a lot of those rocks to be plotted below the curve. And as you can see in the split, it becomes even more of a smattering, I guess. Looking at the red circle down the bottom there, again, those porous rocks, as previously mentioned, have a reduced density, and they also have a lower P-wave velocity. And on your green circle here, we see the effects of veining, where cross-cutting veins distort the velocity measurements, but have such a minimal effect on the density values as the veins comprise such a small percentage of the core's overall volume. And of course, summing up those are actually from the Rocklands, as we just saw in the presentation of the vein there. So, all right, some individual data from a single system. We've chosen Swan here. We have about 1,138 density and mag sus measurements all plotted up on our Henkel plot to the left there. And they're coloured using the iron oxide content, which we obtained from our portable XRF on the MSCL. Unsurprisingly, we see that iron is what dominates the high mag sus values, as well as influencing that density. On the bottom plot, we're looking at our acoustic impedance, and if you sweep, you can see the points are also shaped, and the triangles have been logged as a breccia, and our rectangles are logged as the Swan diorite. You see a clear decrease in velocities of the breccia compared to the more competent Swan diorite again. On the right, though, we've followed up our points using our shortwave infrared and thermal infrared data from the high logger, and we see an abundance of amphibole in both bands of the Swan diorite unit. This information, coupled with the petrophysics, suggests the unit may more accurately call it gabbro rather than a diorite with that amphibole abundance. Cant Adams, our colleague over in CSIRO, has also inserted that little ternary diagram there. And all he's suggesting there is that the mineralogy composition and structure is what controls the geochemistry, and it is that which ultimately influences the petrophysics. And he'll gladly talk with anyone who wants to disagree. And meeting, then all this and more can be found in an upcoming report by Cam from the CSIRO, which is currently under review. Following that publication, we'll be releasing data companions for each deposit hole to provide a ready-to-go document with the lithology, depths, spectral information, and physical properties plotted side by side. There'll also be a brief description of any geophysical implications in the data, and also by various plots, the angle and the acoustic obedience will be provided for each hole too. The data itself we're expecting to release before the end of the year. There's some very in-depth QA and QC and many iterations of processing to ensure that the data we collected are as accurate as can be, and composited with meaningful data to ensure it remains useful in the future.
Are there any questions?
For magnetic susceptibility, do you have a measurement that allows you to know the polarity of the response? I think about analytical signal and see if you have a core that is oriented.
Yeah, no, none of the core was oriented, and
Okay.
yeah, even when you bring on the boats, you can change the way that you orientate all of that whole core, especially it's depending on how it's going to come on, but we did a lot of it didn't have the ability to measure that.
Okay.
Yeah, the originality of the back stuff. What are the grades today?
Interesting. So apart from doing the mineral deposits, have you done any sort of like exploration prospects where, someone's drilled a hole in your EM target, did petrophysics on that to see why there was nothing there?
No, I would love to. Maybe there's one of the deposit studs have one in the anomaly associated, we can dig out and kind of have a look with some of that. The electroresistivity, unfortunately, tools, it's only very receptive to your conductive units, but all the resistivity between doesn't differentiate very well. So it's only when you do get those big massive sulfides that really kind of sort of ice. Yeah, well.
Quickly, are any of those near misses? Those holes just falling off my question?
I will have to get that to you on others. Yeah. And that's certainly where we see a lot of petrophysical data being useful in the actual next phase of exploration, vectoring towards things, and even in a mining sense, you can use petrophysics to kind of follow your body.
Any other questions?
Yeah, that hard work for collecting the data has been around for a long time now. But obviously it hasn't been widely, I guess, taken up by industry or others collecting physical data. Is there any kind of feedback having used it for that year that you give on how to make some of these things like that?
So much, yes. You definitely need an experienced operator, and a lot of the needles and a lot of the instruments as well had to be worked out, and they're still being worked out as well, which is why we've gone through so many iterations of the processing, because it has been over almost 18 months since we released the data. So yeah, there's definitely a lot of things that we kind of look at changing next time. Oh, absolutely, yeah. And they've got 25 years as well with how they can change some of those things, particularly in the electrical space.
I've just got a question about the data that comes out. Can that be directly compared to other physical data collection techniques, and so you can have a wider spread of
the result.
It can definitely be compared, but you're gonna have to know more about the data you're comparing it against to be able to, I guess, get that kind of leveling kind of thing. So, yeah, if you can go back somehow with the data set you already have, some of your information about that. And maybe some transforms you can do to kind of make it a good one, yeah.
All right, wonderful. Thank you, Roger. Ready, Mark Gordon leads the Geoscience Information Management Team at the GSQ and has more than 20 years experience working across digital. Mark has overseen projects such as the Digital Librarian AI Proof of Concept, which investigates large language models, which can help make exploration data more accessible and useful. He focuses on improving how geoscience information is managed and shared to support exploration and investment. Today, Mark will discuss the practical opportunities and challenges of applying generative AI to geoscientific problems. Welcome, Mark.
Thank you, Heather, for that wonderful introduction. It's fantastic. So good afternoon, all. Interest in generative AI has really, it's been growing steadily, particularly in geoscience over the last couple of years, but I think over the last 12 months, it's really gone exponential. And it's gone that way for very good reason. We're in the midst of a perfect storm that's really driving AI adoption in geoscience. And today, I really want to unpack a little of this and give you a bit of a sense of where this is heading, as well as talk about where the GSQ is currently invested in this space. So just to get started, I wanted to make a few comments regarding drivers and uptake and investment in these technologies. And there's a number of things I'm going to comment on next. These are just, it's not meant to be an exhaustive list, but these are things that just really came up for me when I was doing the research for this presentation. We've got this unprecedented demand for critical minerals, which we are all in this room patently aware of. But the difference here is that this demand is for critical minerals, not just from anywhere. It's about finding more critical minerals here at home to drive sovereign supply. And that ups the ante in terms of complexity. In addition to this, geology is not just the only starting point. Finding critical minerals near existing infrastructure clearly has huge benefits. You know, for example, looking at legacy sites with a new lens, it's a real draw card for explorers. And finding repeatable patterns in our data to reduce risk has never been more important for investors. So fundamentally, better use of data can really help us overcome these challenges through the application of advanced machine learning and generative AI to really help us make better exploration decisions. The key point here is that data is the new frontier. It's not just geography. And it's about generating new insight through connecting all of our data together to find that elusive needle in the haystack. The ability to analyse hundreds of layers and millions of points all at once is really beyond human capabilities. But this is exactly what these technologies really excite. So in terms of exploring our data, I believe we're only just getting started. There is so much value that we still have, or so much potential still left in our data in our existing data sets. And the GSQ is really well positioned to take advantage of that, with 70 terabytes of geoscience data really freely available through our open. And to back this up, there's an ever-growing list of compelling use cases. I've just picked a few examples here just to illustrate the point. Basically did a Google search. And the thing in common with all of these examples is that they've used machine learning and generative AI to make significant discoveries. So this example from Royal Metals found significant intersections using machine learning and generative AI only 50 metres from historical workings. Earth AI and Legacy Minerals, through their proprietary AI model, they found the first ever magmatic PGE nickel copper mineralisation within the Lockwood Fold. And Southern Cross Gold at Sunday Creek, they used machine learning and generative AI to identify more mineralisation down dip of their existing workings, as well as identify more prospective areas east of the current mine. So these approaches are quickly becoming integrated across the exploration lifecycle, and they range from the ability to analyse regional data and set up decision layers to focus down or focus effort on specific areas, to the ability to uncover more mineralisation in existing systems, and even by and as well allowing a fresh take on old mine sites. So today's about generative AI. What are the really key use cases today for generative AI? There's a lot of promises and a lot of hype, currently out in the media about generative AI and what it can do. So what is it good for in geoscience today? Well, text summarisation is a really important component of that. The ability to go through thousands of reports and surface insight. Entity extraction and tagging. So this is identifying commodities, formations, coordinates, concepts like that throughout a large data corpus and surface layers and bring those together. Contextual search and insight discovery. So this is about having a conversation with a generative AI capability and having that conversation in natural language. And this is where prompt engineering comes in and is becoming a really important skill. And we're going to talk a lot about prompt engineering tomorrow in our generative AI workshop. There's also knowledge graph generation, and this is about turning unstructured data into a structured form. And this generates new knowledge through the ability to link concepts through relationships like deposits, rockiness, elements, events. There's also cross-document synthesis. So this is about aggregating observations across reports. So not just within a report. So if you see something you like in a report, you can ask the capability to go out and say, find me more of this. And what are the key benefits, really, when you boil it down? Huge time savings in retrieval and lit review. And what does that mean? Well, it really means more time for geology. For doing the science. It also can improve data discoverability and knowledge reuse. And this means, as the anecdote I used earlier, finding that elusive needle in a haystack. If you've got thousands of documents to read through and hundreds of pages each, there's a better chance using generative AI if you might find that one small thing that's going to lead you to that next discovery. And I think most importantly, it's a great foundation for next phase applications, but not necessarily just the means in itself or an end in itself. It's about taking the insight that you find through this particular process and then feeding that into something like a machine learning prospectivity workflow and adding extra value to that particular process. Okay, so how's GSQ investing? What's our role in this? Well, our key focus is and always has been about using all the data and getting the most from what we actually have. And generative AI, at the moment, we're focusing very much on the text. Unlocking value from our vast data archive, we've got 100,000 industry reports in our archive at the moment. So how can we use those data? How can we surface and extract insight from that collection? We have an ongoing commitment to data science, and it's been about, particularly the last 5 years, baking data science capability in from the ground up. And we're moving, there's a bit of a paradigm shift that's happening at the moment. We're moving from metadata search, that is where you're basically through the open data portal searching for data resources through the metadata against those data resources, to a search where you're able to interact directly with the content. Now, I'm not saying metadata isn't important. In fact, it's really important in the age of artificial intelligence. But both of these things complement each other. And we've also got a strong focus on data quality, and it's a key success factor for AI. And I'm going to talk a little bit about more about that a little bit later. We're also exploring the technical potential and benefits through something called our digital library and proof of concept. And this is really focused on extracting summaries and insight from critical minerals industry reporting. And again, I'm going to just unpack that a little bit shortly. We're also building capacity and capability, particularly from a governance and a business readiness perspective. Proof of concepts in themselves, and there's a lot of people playing with AI at the moment, they don't really scale well without these elements. The business has got to be ready to accept them, and you have to have appropriate governance over the top of these capabilities for them to be successful. And your return on investment isn't just in the technical implementation. It's also in how it changes your business and the opportunities that provides for you. We're working towards this vision that I call decision-ready data, which is all about having embedded insight. And what do I actually mean by that? Well, it's about not just having data sets published on the Open Data Portal web that you can download and I guess review. It's about having products that are focused around things like commodities or systems or areas across the whole arc. And the GSQ is already doing this at the moment. Vlad's team is heavily embedded in this particular space. But the difference that generative AI makes in particular here is that it enables us to scale that over hundreds or even thousands of commodities, systems, areas, and concepts, which is the real opportunity. I'll just give you a bit of a quick review of the GSQ Digital Librarian. This was a project that it's actually been in place now for about 18 months. It's an internal proof of concept. It was a couple of years ago we were thinking about how we could use generative AI for geoscience. And we weren't really sure 2 years ago how successful it's going to be. I mean, 2 years from an artificial intelligence development point of view is an absolute lifetime. But at that point in time, we weren't sure about whether this was going to be successful or not. So we thought we'll have a crack, we'll stand this up and see how it goes. And it's been a really successful tool. It's been successful for a couple of reasons, really. The first is it really proved the technical capability of using a large language model, to query industry reports. So technically, we were quite amazed in terms of the insight and the detail that it surfaced. I think the second thing about this that was really successful has been the ability to drive conversations around generative AI across the organisation. I guess get the organisation ready for production, publication of this kind of capability. So basically, it's a very simple interface. It's sitting over the top of about 3,000 critical mineral industry reports. You can select a persona. I think you can see that pretty well there. A standard geoscience user. You can be an exploration geologist. You can be a student. You can't be super banned at the moment, but if you send me enough emails, maybe we can get that included. And you can also select a geographic. Well, something's happened here. Sorry. Does that come up? Sorry. Yeah, you can actually constrain it to a geographic area. So if you're interested in searching reports from a particular geographic area, you can do that. And basically, you can just ask a question in natural language, and it will keep context. So you can ask it a series of questions if you like, just for the purposes of this, for the presentation. It's got one up there, and it will produce this nice little summary, which maybe half a dozen points or so related to the question, and it will also then give you a reference to the report in which that piece of information came from. So you can actually validate that. That's great. Excuse us. It's always a technical glitch something. Yeah, no worries. All good. Okay, so this is really all about providing, and it's focused very much on the use case around an exploration geologist coming into a new area and wanting that has to review a whole heap of reports. I think it's still transcribing. I'll just keep going. Yeah, so in terms of being able to analyse and get, I guess, a good look at what what reports are available, what's in those reports, and interact with that data corpus really efficient way. Okay. So given the success that this particular tool has had, one of the things in our mind is that we really like to potentially productionise this and offer a service like this through the Open Data Portal. We think it has a lot of validity. But I think the thing that we really need to do next is to collaborate with industry around what this particular tool should actually look like. Is this the kind of thing that industry would want and needs to use? And we need to understand things like what questions would you ask, what features should it have, and I think we really like to surface some of the benefits that this kind of a tool might have for explorers. So we currently have a survey out, and I'll have a link on the last slide of this presentation, so please get your cameras ready. But I would like to hear from you in terms of what you think a tool like this should look like. We've also got a workshop tomorrow, which is an opportunity to feed into this particular process, and tomorrow's workshop's not just about feedback. There's a lot of other things that we're doing as well, around prompting and how you can actually use existing tools for geoscience. So we've got a value-packed agenda. And we'd also like to establish an industry Gen AI reference group. And the reason that we'd like to do this is really around how quickly AI is actually moving. If we were to sit down, design and put a tool in place that took 6 to 12 months, it would already be out of date before we finished it. So this new paradigm that artificial intelligence is putting in front of us is that we need to work much more closely together. We need to have much faster, agile, quick development cycles. So as capability becomes available, we can quickly test it and release it. So the key goal eventually is to establish some kind of industry pilot. I can't have a conversation about generative AI without really talking about data quality. I think it's so important. And as good as generative AI is at surfacing insight, it's equally as good at amplifying information. So models can reproduce and magnify errors, gaps, and biases and hallucinate, basically. Just make stuff up. Content is everything. So consistent metadata, and I was talking about the importance of metadata earlier, it really means clarity of context. And it's not just about having vocabularies in place that really explain all the concepts that you're wanting to talk about. It's about being able to vet input data sets for compatibility. So coordinate systems is a really classic example of that, or collection standards or those kind of things. It's about having provenance, so knowing where your data comes from and understanding how it's been collected and how it's been changed over time. And it's about having human in the loop, having Gen AI must be explainable, so therefore the data sets that go into it have to be explainable too. And it's about having a chain of human accountability. Who approved the data set, who validated, who's accountable for its use. So it's just, oops, sorry. So traditional data governance done well applies here too. It applies here as well, and that's true pretty much of any major digital initiative that you might care to choose. So what's the GSQ doing around in the data quality space at the moment? Well, working more closely, we really want to work more closely with industry regarding the quality of industry reporting. I think this is a huge untapped opportunity. Industry reporting is highly variable in terms of its quality. It's done very well in some cases, it's done less well in others. And being such a valuable resource, and for data quality being so important to artificial intelligence, particularly generative AI, if there's an opportunity for us to improve that, I think we should take it and work together in terms of improving that particular outcome. And I think that's something that we could address as part of that industry reference group. There's also the GSQ curated dataset program, and this is about producing data science ready datasets for model inclusion. and how we apply, and we're actually looking at using artificial intelligence to actually help us create better versions of data sets. Like geochemistry is probably a prime example of that. Ensuring all our data is fair, that it's findable, accessible, interoperable, and reusable as well, and that goes without saying. And I think, in my very humble opinion, data quality is really the single greatest determinant of Gen AI implementation success. Again, that's why we need this collaboration. So the key takeaways from today: data is really our new search space. I mean, data's always been important. It's always been part of the geologist toolkit. But the difference now is that these new tools are unlocking unprecedented value from data sets through the ability to combine, create relationships, and really dive into the data in a really deep way. Gen AI augments expertise, and the key word there is augments. It's not about replacing geoscientists. In fact, the best results come from when geoscientists work with these particular tools. It accelerates interpretation and knowledge discovery. I've made some comments already about data quality, but really, again, if you want reliable outputs, you've got to have good data going into these particular models. And the digital librarian has really proved the concept. It's really a definitive use case which can be used for more future opportunities, and that's what we really want to do. Again, collaboration will really amplify it. I've said that a few times. So questions? I'd love to hear from you. Bottom left of the screen there is the nomination link for our Gen AI workshop tomorrow morning. And on the right, we have again a QR code for our Gen AI Super Day. I mean, this technology is still evolving. And so are our ideas about this. So really keen to explore together. Thank you very much.